Hello and welcome to the course Basics of Experimental Design for Cognitive Psychology. I am Dr. Ark Verma from the Department of Cognitive Science at IIT Kanpur. This is the third week of the course, and in the previous lecture we were talking about mechanisms or mechanics of experiment design. So, we started with the model m of x is equals to b of x plus an error term, and in the previous lecture we sort of learned 2 to 3 different sources of where errors can come from and why do we need more measurements. We talked about error within participants, changes across trial within the participant, error between participants. If you have more participants, what are the sources of errors that happen and why, how can you sort of minimize that in getting closer to this b of x, which is the perception action loop. And the third was E of C, which is conditions. So, if you have different levels of a given factor that is your independent variable that you want to study in more detail, then also across conditions there is going to be error or variation in this b of delta C, or basically the change in the mental process in response to that difference in the two conditions. Okay, that is what we are typically after. So, that is why we sort of manipulate variables, have different levels of them, and these variables, the effect of these variables is what we are actually after. So, we basically talked about these three things. Let us continue the same and let us try and understand how things go further. Now, one of the things that we can talk about is that when we are having different conditions, or say for example, when we have different levels of a given variable, there is not only, or sometimes there is a change in the condition where the two conditions are extremely different, but there is sometimes this transformation of condition A into condition B. Let's talk about this, and how would that possibly affect mental processes, how would that possibly affect the kind of thing that we are trying to measure in our reaction time experiments. Alright. So, if you have two conditions in the experiment that differ along one dimension, let us say contrast. In this pointing example, we talked about 50% contrast or 100% contrast, or let us say you have 0% contrast, 50% contrast and 100% contrast. Across these different conditions, obviously there will be slightly different b of delta C, slightly different mental process that has taken place. Now, this b of delta C is basically going to talk about, or is basically going to represent the change in the mental process with reference to the difference in these three conditions. Alright. So, that is basically what basically what we are after, but experts sort of, the idea, the evidence kind of suggests that we cannot still talk about what is really happening in the brain, what is really happening in the mind with respect to these things. Why can we not do that? Because let us say in the first case, let us this 100% contrast or 50% contrast thing, the experimenter had only two conditions. So, we can talk only about those two conditions. Let us say you have three conditions 0, 50, 100, then you can talk only about three conditions. You cannot talk about the fact what happened from 0 to 50 or 50 to 100. You can talk about what happened at 50, at 0, at 100, but you cannot talk about the effect of this change on mental process. Alright. The second reason is that, as I said, we are talking only about the difference, but not about the transformation between these conditions. How does the mental process change between the two contrast conditions? Okay. So, talking about the perceptual effect of changing some variable, in this case contrast, would actually require that the participants see this temporally transforming, see the particular stimulus changing in time with respect to contrast, tying to this example. Okay. Now, since in this case the participants see only two levels of this particular contrast, so 50%, 100%, we can talk about the effect of one condition in terms of its difference from the other. So, 50 basically this is what you get, 100 basically this is what you get, but you cannot talk about how these two conditions are one transforms into another. Okay. So, this result of our experiment, if you basically compute across conditions, will inform you about this b of delta C, this effect of 50% difference in contrast, but not really what happens in these two levels. As the participants did not see the transformation from high contrast to low contrast, we cannot be sure about the perceptual properties or the perceptual consequences of contrast change. Okay. Now, for that reason a lot of times what we do is we create what are called symmetrical experiments. What are symmetrical experiments? Let us say you have this 100% contrast condition, you can talk about that as the baseline condition, and then you can have the 50% contrast condition, which is basically will be referred to as the experimental condition or so on. Now, in the hypothetical pointing experiment, both conditions have all the same elements, but only one factor is changed between them. No dimension is added or subtracted. Okay, it is exactly the same, just contrast is different. It is the same dimension, it is just having two levels, that is different. This means that we can use either of the two conditions as a baseline. You can use 100% as a baseline for understanding what happens at 50% contrast, you can use 50% contrast as a baseline for what is happening at the 100% contrast condition. This is what is referred to as the symmetric experiment. Okay. So, again this is sort of very common, it is not very common to have these kind of symmetrical experiments, but more common is that every experiment has a typical baseline condition and then has variations of different levels. Okay. So, that basically is something that is more common. Let us try and understand what is happening here. Now, slightly going back, we talked about the fact that there are these various sources of error and variation in a participant's performance. Within the participant there is error, there is variation possible, across the participants there is error, there is variation possible, across conditions there is error, there is this variation possible, error and variation being the same thing for me. Okay. It must be pointed out in the sense that it is extremely hard to sort of understand the perception side of this perception action loop, because what is really happening, how is our phenomenal experience changing across these conditions or across these different conditions is something that is not very easily understood. More so, we cannot even directly measure perception, we can measure only the responses that we are getting. Okay. So, we will get changes in values 550 milliseconds, 540 milliseconds, 600 milliseconds, we are getting changes in these response times, but not really what is happening in the phenomenal experience. Okay. So, basically that is one of the reasons why this B of x is taken as a substitute for whatever is happening. So, this variation in B of x is basically taken as the variation in both the phenomenal experience and the response that is basically happening. Now, if we look closely, it will dawn upon us that the only way to measure the perception side of this perception action loop is that you basically divide the B of x into two parts. First is perception part, looking at the stimulus, and second is Rx, which is basically the response strategies. Okay. So, strategies, memory, decision, motor activity, other factors. So, you can still say there are two parts in this B of x that we want to study. This will get much clearer when I talk to you about experiments in some detail. Underlying assumption shall be that perception is in fact independent of everything else and its effects are linearly additive to it. So, basically what we are saying is that if some responses are difficult or easy to make, we can still have this additional. Remember Sternberg, you are basically adding steps in reaction time. We will talk about the subtraction method at some point. Even then we would need to construct two conditions or situations that are absolutely identical in terms of literally everything, just this factor changing. That is how you will be able to calculate the effect of that condition. Okay. That is where multiple levels of a factor come in. Now, previous experiment we had 50% contrast, we had 100% contrast. Remember we were talking about specificity and generality, exploring the nature of a function. So, if you are sampling 2 points, one at 50%, one at 100%, how does that place you in terms of estimating this overall function, the nature of the overall function? Let us talk about that. Okay. Now, in principle with these two contrast points, we can extrapolate and it will be able to provide us with a reliable estimate of the values near 50%. So, let us say between 55 and 45% contrast, what is going to happen can be sort of estimated by the participants' performance at 50% contrast and around 100%. So, around 90 to 100 whatever is going to happen, we will get from that level. Okay. So, but we need to be able to generalize across this whole dimension, what is happening at this range of contrast. We are taking this as a continuum from 0 to 100%. Okay. So, we will need to choose several contrasts along this entire range of possible contrasts, and these points should be close to one another, so that we can allow for good interpolation, but also far enough because they should be able to give you the overall nature of the function also. Okay. So, how do we do that kind of sampling or hedging at the level of factors? So, let us say if we wanted to sort of be able to talk about this entire dimension, we might choose, let us say we start with we have 0 to 100. So, we start at 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So, we will have 11 levels. Okay. Now, since people will not be able to see this 0% kind of target, so we leave it and we are still left with 10 levels. So, we have 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So, we have 10 levels of contrast. Now, since there is only one factor here, we are just varying contrast, everything else is being kept identical, the number of conditions is exactly the same as the number of levels, because one factor only. If there were two factors and so on, we will multiply that, but at the moment we have only one factor, so it multiplies by 1, stays exactly the same. Now, when you are creating the stimuli, the experiments will need to take care that each of the 10 conditions is otherwise identical to each other. Okay. There should be no difference in these 10 conditions other than the fact that the contrast is different, nothing at all. Okay. So, also what we will do is we will measure each of the several participants' behaviors or responses several times. So, at each condition we will take several measurements, let us say 10 measurements, 20 measurements at each condition, and because this is a symmetric design, each step differs from each other in just just 10% contrast. So, you can take any of them as a baseline for any of the other conditions. Okay. Since again that is what I am saying. So, since the basic change along the factor is just a 10% drop in contrast compared to baseline, we can represent all the changes in the stimulus with a single variable p, one step 10% contrast level difference, and basically at step 1 it is just p, step 2 it is 2p, step 5 it is 5p, and so on. Now, by comparing the performance of the participants in any of these conditions, we can precisely determine the effect of the specific contrast increase or decrease. So, you want to come from 100 to 0 or 0 to 10, you can basically figure it out in that sense. Now, since this is a symmetric design, we can compare performance in any one condition compared to any other single condition. So, how do we sort of determine that? You see here we have this m of x, b of x has two error terms within participant, between participants. This is the effect of that delta we were talking about, that delta in difference in contrast. So, x1 minus delta p, x1 minus 2 into, so this is the second step. Eventually, you have the 9 steps. Basically, what you are going to get is that you are basically going to get at every step when you subtract the effect of one step of contrast change. So, the input to both the measurements m and this perception action loop are represented, let us say in terms of this base condition of x and multiples of 10% contrast change. So, this is what we were seeing in this equation here. Now, while the input to this perception action loop is indeed periodic, there is no guarantee that the output is also exactly symmetrical or exactly periodic. We do not know. For example, how do we change the the sound, when you increase sound on your television or something, volume 1, 2, 3, 4, 5, are they exactly 1 step, 2 step, 3 step different, or they are exponential? Remember, we have talked about that. Okay. Now, performance may not differ much between 100% and 50%, but it will be drastically different between 0% and 50%. So, we sort of get that. In short, a constant change on the physical side does not necessarily reflect the same constant change in the psychological or the perception action loop style. Okay. Now, we had 2 conditions previously, now we have around 10 conditions. How do we estimate the overall function? Look at this, it is possible that there is a steep change from 50 to 40 to 50%, or there is a linear change from 40 to 50%, and this basically gives you an idea of how this function is going to be. It gives you, say for example, if you have sampled well enough, just like in this example, there is contrast percent, so there is this the same pointing error on the y axis and contrast changes in this x axis. There could either be a very drastic step difference between 40 to 50%, or it could be all just in linear terms, 10 to 20 the same change, 20 to 30 the same change, 30 to 40 the same change, and so on. Alright. So, again remember, how are we sampling, or at what levels we are pegging up at a factor? basically might not reflect in exactly the same way in the response times, but you will need to have, say for example, in a lot of studies when you are trying to look at the effect of SOAs etc., or say for example presentation durations, a lot of time you will see people have a range of time periods of presentation. So, 17 millisecond, 34 millisecond, 51 millisecond, 68 milliseconds and so on. So, you sort of sample across this overall range if you want to, let us say, understand the level of understand the effect of the presentation duration of a given on the recognition times of a given stimulus. All right. Now, among these different conditions, let us say you created 2 conditions, or you created 10 conditions, or you created 3 conditions. What is the effect of these different conditions on how the participant, and which condition the participant is seeing first, which the condition the participant is seeing second, and so on. So, these will be referred to as order effects, and how do order effects play out? Let us try and study. Now, in a general sense, what participants see or do on any given trial may actually have an effect on how they perceive the next trial. So, here if I see 50% and the next one is 100% versus here if I see 50% and the next one is just 40%, there is going to be a slight difference for me both phenomenally and maybe when I am making my responses. So, this difference between the 2 conditions might be either just due to the contrast or the order of presentation, or say for example, the experimenter getting used to or not used to this delta between the 2 trials. Okay. That is basically what leads to what are called order effects. Okay. So, not controlling for order can sometimes therefore act as a confounding variable. Now, how do we control for order? How do we sort of talk about this? Now, there are 2 or 3 ways in which we can do this. First is, the experimenter could try to explicitly control for the change in order if and see if it has any influence on our measurements. This can be very easily done through a between participants design. So, you can have a AB, ABBA, ABBA, ABBA kind of design. This could be achieved. So, this is basically the between participant design. In such a design, each person sees one and only one level of one factor, one condition, although, so for example, there is one condition in which he might see multiple repetitions of that condition. So, one person is seeing just 10%, 10%, 10%, other person is seeing only 20%, 20%. So, between, and then you compare these 2 people or these 2 groups of participants. By ensuring that each person is seeing only one condition, there is no order of conditions and therefore, there is no order effect. So, it is not the ABBA kind of thing, it is one group seeing just the A, other group seeing just the B, and you are comparing between the A and the B. That is basically giving you the difference between conditions, or because there is no order, you basically broadly compare these 2, all right. But in this case, the difference between the 2 conditions now reflect the changes in contrast and also across participants. Whatever difference you will find, you will be, say this group has seen only A, this group has seen only B. Yes, you will get the difference of the difference in conditions 50% and 100%, but because these are different people, you will also see the error term getting affected or influenced by the difference between participants. So, that basically becomes a bit of a problem, all right. So, this design typically will rely on the relies on the assumption that the between participant variance is small. The higher this between participant variance, the lower will become, I mean your ability to estimate B of x will become lower and lower. Okay. So, in that sense, this is not the ideal thing, and that is why you will see that in a lot of studies that are comparing across conditions, because the error is slightly larger than in the within participant situation, you will need more sample size. Okay. Now, let us say the between participant error does not show up if we measure only one person, obviously, because there is the same person. So, if each participant sees both the conditions or all the 10 conditions in this last example, then any difference between the conditions will not be due to the between participant error, but will only be due to the difference in these contrast steps, the baseline. So, 10% versus 20%, 10% versus 50% and so on. All right. So, a condition where each participant sees all the conditions, that is every level of every factor, is referred to as a within participants design. Okay. So, earlier it was between participant, here we are talking about within participant design. Okay. So an approach could be to avoid order effects is to treat contrast as a within participant thing. So each participant is seeing all the levels, so 50% also, 100% also, and order as a between participant variable. So for example, what will happen is that different groups will see this in different order. So one group will see AB and the other group will see BA, all right. So 50% and 100%, 100% and 50%, or say if you have more, then you can work with that. Now this would allow the participant to sort of remove the between participants error, the EB term in determining the effect of contrast per person, but this also has another issue of its own. We will talk about this now. Okay. So between participant noise will still be there, it will be present in the order effect. One group has seen AB order and the other group has seen BA order. Okay. If the average within participant effect of contrast is different between the two groups, let us say there is some error that is arising out of because of order, and order is still a between participant variable, it might be due to either differences between groups or differences due to order. So order can sort of play a part. Now to control for the same, many participants will be required in each group. I just said as many groups, as many number of participants you will need. While this approach provides a relatively cleaner measure of the effect of contrast differences, it comes at a cost of potentially large number of groups. Just for this previous experiment that we are talking about 10 levels of contrast, it will actually require us around 36 lakh groups to properly study. So the number of possible orders is x factorial. So x being the number of conditions. So you have 10 conditions, those many trials you will require. Okay. Sometimes what people do is they say, okay, these many trials are overall required, but we will just sample a small subset of this and we will do it. But again, you will see that this is not a perfect condition. So a final approach to avoid these order effects could be that each participant sees every contrast in a different randomly chosen order. Okay. So what happens is, now once you have randomized this order of trials, it would convert the systematic order term or the error, because that is coming out of a systematic AB or BA variation, into another noise term, and as with other noise terms, if you take collective measurements, this will eventually reduce and go out of the equation. Okay. That is why what you will see is a lot of times we have a randomized presentation of trials. Okay. Why do we have a randomized presentation of trials? To take care of order effects. You are taking many measurements to take care of within participant error, you are taking many measurements to take care of between participants errors, and you are basically having randomized presentation of trials to take care of order effects in these experiments. So let us say that we are sampling from the many order group that are possible in a fully controlled order experiment. Again, because of an additional noise term, this will also slightly require more participants. If you have more conditions, you will need more participants. Okay. Now another thing is that a lot of times we need more factors. Okay. We are typically not working with just one factor. Say for example, in the previous hypothetical experiment, we had just one factor, contrast, it had 10 levels. A lot of times you have more factors. You say for example, you can have, in the laterality example, you had one factor was stimulus, the other factor was visual field. So you can have two factors, sometimes three factors, sometimes more. Okay. That will also bring its error term. So let's see, let's try and study that. So let's say if you want to vary target size. Okay. This is this bullseye. There is this target, the target is of let us say 5 millimeter or 10 millimeter or 15 millimeter, we want to study that as well, and we have the contrast variable anyways. Okay. So we have two measurements we will need, one with a small target m of x and one with a large target m of x plus delta s. Delta s is basically the difference in size. Okay. Thus we will have one factor with two levels, big and small, which will give us the following set of equations. You can sort of pay attention to this. Now if we want to measure both size and contrast, so we have more factors. You will have x plus delta s and you have x plus delta p, which is the effect of contrast. Remember we are talking about contrast change in steps of 10, 1 p is equals to 1 step, 2 p is equals to 2 steps, and so on. So a full factorial combination will basically lead to us having two factors with two levels. So we will basically have a 2 cross 2 design. A full factorial combination of the two factors will give us 4 conditions, 2 contrast levels for large targets and 2 contrast levels for small targets, each of which will need to be measured. So here we are sort of measuring b of x and b of effect of change in size, effect of change in contrast, and anyways the typical error term within participant and between participants. Now, remember these equations 2.16 to 2.18, these basically explicitly include terms for size differences and contrast changes, as well as they have the typical there is also, by the way, have a term which is the interaction between the two variables. Okay. So, we have those as well. This basically will allow us to examine the factors in that are linearly separable or orthogonal and strongly resembles the general linear model that underlies one of the common statistical perceptions. So, basically this is what we use what are the underlying assumptions, that why we sort of carry out ANOVA analysis of variance and so on. All right. So, I will stop here. Again, we have talked about some of the mechanics, some of the very basic principles in experimental design. I will take this forward in the next lecture, and let us see how it goes. Thank you.